Before we jump into the analysis, we need to learn a new approach to thinking about waves. And I'm probably going to mispronounce this, but I think it's Huygen's principle. Um, and this dude lived a long time ago, pretty much the same time as Newton, and a mathematical model for waves didn't exist yet. So this is an alternative view to thinking about waves compared to everything we've done so far. Now, in all of my physics studies, I have rarely used this. It's something that exists and that in some situations is really, really helpful, given the fact that we have a lot of other tools now. So we're covering it now because it's really the most helpful way to understand single slit diffraction. It doesn't make a lot of sense to analyze single slit diffraction without using this model, and in general, this makes sense for diffraction overall. We do have mathematical tools for understanding diffraction beyond this. However, those are beyond the scope of this class. So this is a historical understanding of waves. We can use it especially for diffraction, and it prevents us from needing to do some really complicated math. So the basic idea is that we take a wavefront, remember our good old wavefront, since these are parallel, this would be a plane wave, and we imagine that every point on the wavefront is a source of a wavelet. Now the wavelet then, the source is in pink, and the wavelet is also in pink. It's the circle. Now, obviously these could be spaced differently, but we're just going to pick some of them. But we're aware of the fact that this being just really a visual representation or a conceptual approach, that there's nothing physical here per se. But then we say, okay, now at this point on the wavefront, these little wavelets start expanding, that they're spherical waves if it's 3 dimensions or circular waves if it's 2 dimensions. So these wavefronts expand outwards. So we're looking at some point later in time, that at an earlier point in time we had this wavefront, so we called these points on its sources. We then let these little circles expand out. You now see at a later time that there's this line here, this new wavefront, which is tangent to all of them. So that's the basic idea. And again, it's not going to make a lot of sense until we apply it to a phenomena that we didn't have a different method of understanding. But let's look at a different geometry first. So this is the geometry we just did. We had a wavefront. It was a line because it's a plane wave. We plopped down our sources for our little wavelets. We saw at a later time that our new wavefront was tangent to all of the circles. We can do the same thing with a spherical wave in 3D or circular wave if it's 2D, where we have one wavefront at one moment in time. We drop down points representing sources of our wavelets. We then let those little circular wavelets expand outwards, and we again then draw our new wavefront being tangent to all of those wavelets. Now notice here, it's not exactly tangent to a circle, but had we doubled our number of points, right, and actually put additional sources, I'm not going to draw all of them, but you can see that now we would have actually another circle here around these new points. So we have to interpret a little bit in our head, given that we're not drawing every single point, but you again see that our wavefront that we before have just been generating is made up of the tangent points to these wavelets. Now, the wavelets are also going to be allowed to interfere with one another. So that's going to be in our next part of the analysis. But notice that here you would have constructive interference. Here, well, these wavelets haven't gotten there, so you of course have constructive interference. But there would be places between these different wavefronts where you actually do get destructive interference. So again, we're not normally going to talk about it that way, but you can kind of think about these wavelets as interfering with one another. That is still part of this. So what this really helps us to do, in my opinion, is think about how waves are spreading out. And this is going to be important for our single slits. So in our single slit, we have a plane wave that is coming in and hits this slit. Notice this would be a really, really small slit, again, a millimeter or something like that. But now we can imagine that as the wave front passes through the slit, that we drop down all of these sources, which are now generating these little wavelets that come out. Now, in this case, they're not just complete spheres because it's kind of blocked a little bit, right? It's literally blocked here. But you can see that it can come straight out. Now, this isn't a ray model, but it's still the notion that this is a barrier and our wave can't quite pass. But once this edge of the wave is traveling that way, it can keep going. So this actually answers the question of how is the wave spreading out? Notice that our wave is getting bigger and bigger. And this is again a little bit different from just something like a shadow, because we haven't considered the distance that our source was away. It was a plane wave. We uniformly illuminated this. So this is fundamentally a very wave phenomena. Now we can still get interference between all of these different little wavelets. However, remember that if we drop more wavelets down, some of that interference might change, but you're still definitely getting a wave front here, a wave front there, a wave front here. And dropping more sources down here doesn't actually change what this edge is. So we are going to get now interference from these wavefronts on our screen, and that's how we actually understand the pattern that we get from a single slit, where we don't have multiple real sources to think about, but we can use Huygen's principle to basically generate these artificial or virtual sources that we then think about as generating their own little wavefronts.